Hi everyone, this is a set of video solutions to a recent probability quiz we did in Year 12 Theatre Maths. All these questions come from past HSC papers going back to 2001 to about 2007-ish. So nothing too recent, although seeing that the current Year 12s are still doing a course that hasn't been changed in decades, it's still all pretty relevant for advanced students in years to come. I'm sure there's probably some kind of relevance to some of these questions too as well. So these questions will be pretty useful. So let's just start right into it. We see question number 1. The packet contains 12 red, 8 green, 7 yellow, 3 black jelly beans. 1 jelly bean is selected at random from the packet. What's the probability that a selected jelly bean is red or yellow? So that was just a typo by me as I was transcribing the question, but whatever. Continuing on. So we see that we add up all these numbers, so the 12 red, 8 green, 7 yellow, 3 black, that equals to 30 jelly beans, so there's 30 in total. And so if we're choosing out this 30 in total, the probability that it is red or yellow would be the probability whenever we're thinking the word or, we add. So the probability that it's red would be 12 over 30, and the probability that it will be yellow would be 7 over 30. That leaves us with 19 over 30. So fairly simple one to start us off, and that's a 2 marks question as well. So quite forgiving, but I mean, this, like, when you look at the paper that this is taken from, this is from like one of the very first questions. I think it was like the 3rd question in the whole HSC. So it is meant to be quite easy. Still, even then, it is quite nice, quite generous, giving it 2 marks. But basically, it's 1 mark for getting the total amount of jelly beans. So if your answer has a denominator of 30, that's 1 mark. And the other thing would be getting the 19 on the top, realizing you need to add the probabilities of those 2 things. Going to question 2, we see that the diagram shows 2 spinners would be spun simultaneously. Each of the 3 outcomes are equally likely. We can kind of see that in the shape. We can see that in that first spinner, they're like cut into exact thirds, and the other spinners cut into quarters as well. So they're all pretty much equally likely. So what is the probability that both spinners stop on the same number? So if we look at these spinners for a second, we see that the common numbers there are 1s and 3s. So really, the only way that we can both spinners ending on the same number is if they both land on 1 or if they both land on 3. So I'll just scroll down a little bit. So for part A, what is the probability that both spinners land on the same number? Basically, we find the probability of 1, 1 or the probability of 3, 3. So I shouldn't write or, I should write plus. So that's going to be, well, the probability of 1, 1 is going to be 1 over 3 times 1 over 4, because if we look back at the spinners, it's a 1 in 3 chance that'll be a 1, and it's a 1 in 3 chance that'll be a 4. So we have that, and then the probability of 3, 3, well, that'll be the exact same, so 1 over 3, so that's 1 over 4. So that will give me 1 over 12 plus 1 over 12, which gives me 2 over 12, which also gives me 1 over 6, if you want to write it that way. So here, basically, this is 2 marks questions. So the first thing you need to do, basically, if at some point you got 1 over 12, or you wrote 1 over 3 times 1 over 4 at some point, basically you're realizing that's the probability of getting the same number twice, realizing that there's 2 options, so therefore 2 over 12, or 1 over 6, is how you get your other mark. And so now if we need to find the probability that at least one of the spinners stops on the 3, so again, looking at it, if we want to find the probability of at least one thing happening, the best way to find it, or the quickest way rather, is to find the probability of that not happening at all. So here, if I want to find the probability of at least 1, 3, so 1, 3, that's going to be the same as doing 1 minus the probability of no 3s. Okay? If we can find the probability of not getting a 3, that means the opposite of that would be the probability of getting at least 1 3. And then so the probability of getting no 3s in this situation would be, if we look back at the spinner once again, the probability of getting not a 3 in the first one is 2 over 3, and the probability of not getting a 3 on the second one is 3 over 4. So we're going to multiply those together because it's an and there. So we've got 2 over 3 times 3 over 4. So that'll be 1 minus 6 over 12, which equals 6 over 12 or 1 over 2 as well. And so you just got to get either one of those. So the answer is just 1 mark, so simply just 1 or 2. Alternatively, what you could have done is find the probability of getting a 3 on the first one and not on the second, find the probability of not getting a 3 on the first but getting on the second, find the probability of getting 2 3s, and that's all the possible things that would be getting at least 1 3. But as we see, that will probably be a longer way. Whenever you got at least one question, generally what you want to do is find the opposite, so of not happening, and then do 1 minus that. So let's go on to question 3 now. Chris has 4 pairs of socks in a drawer, each pair being a different color. He selects socks at one at a time, and his socks one at a time at random from the drawer. So the probability that he does not have a matching pair after selecting the second sock is 6 over 7. Explain why this is so. So this is an explain question, and these are kind of rare in the HSC nowadays. But explain kind of indicates that you want to be saying it with words. You don't need to, you can numerically explain why, but basically you need to explain why it's going to be 6 over 7 for not getting the matching sock. There's plenty of ways to do this, but essentially what you need to say at some point that when you draw when you get the first first sock out of the drawer, there's going to be 7 socks left. So after it's taken away, there's 7 socks, and then once there's 7 socks left over, the probability of getting the matching one, so therefore probability of matching, would be 1 over 7. Sorry, because I mean, say there was like all these different colors. Say if you took out a red sock, there's only going to be 1 red sock left out of the 7 that are in total. So therefore the probability of not matching, because we've got to read the question carefully, find the probability that it does not match. So therefore probability of not match would equal 6 over 7, because it's the opposite. 1 minus 6 over 7. These are just complementary ones together. So now find the probability that he does not have a matching pair after selecting the third sock. And this is quite a tricky question because there's a few things you need to consider here. So I'm just going to write down here. So if we have, if we're trying to find the probability that it does not match after the third sock is taken out, so that means we're finding the probability of not a pair and not a pair. So I'm going to call that P and N. Alright? So it's probability of not matching and not matching. Alright? So they're because we said the word and, we're going to be multiplying. So as we saw in the first question, the probability that after we draw the first sock, it's going to be 6 over 7. And then it's tempting to say, okay, and then once that sock's taken out, so it'll be 5 over 6. And then it's tempting to say that. That's not correct though. When you think about it though, and I might just do a demonstration over the side here for a second. So say I had 2 black socks, I had 2 red socks, I had 2 green socks, and I had 2 blue socks. I'm not going to try draw socks, I'm not going to draw. So let's say I took out a blue sock first. Okay, so if I took out the blue sock first, I got 7 left, and 6 of them do not match. So that's pretty easy, that's why it's 6 over 7. That makes sense. So if I didn't take out blue on the second one, let's say I took a green one second. Okay, so now I've got 6 socks. So we know we're still choosing out of 6. That bit is correct. But the question is saying, find the probability that we don't have a matching pair. The question is not saying, find the probability that you don't have a matching pair from that first one. So what we're saying here is, yes, I can't choose blue, because that's what we chose first, but we can't choose green either, because then we'd still have a matching pair. So really, we're not going to be considering these. Neither of these fit that situation anymore. Meaning that we can only choose a red one or a black one. So there's 4 socks that we can choose from. So 4 over 6. And then, so now that we've got that, we're going to multiply them together. So you could just do 24 over 40. Sorry, not 20. Yeah, 24 over over 42. Try that again. 42, which equals 4 over 7. Or you could have easily just crossed out these 6's across ways and you get 4 over 7 as well. That doesn't work at all. Alright, so basically, the trick to this question is not only to realize that, yeah, we're taking a sock away to make it 6 the denominator of the second one, but also realize that now we've got 2 opportunities of getting a pair now. And so what's the probability that the 3 socks include a matching pair? So if we found the probability of not getting a matching pair, that means the probability that in the first socks it does make a matching pair. It's just going to be a complementary event. It's just going to be opposite. So this is quite easy. So the probability of getting a match would be after the first 3, which would be 1 minus your previous answer, 1 minus 4 over 7, which equals 3 over 7. Fairly simple in that one. And this is another instance of correct for previous answers. Like there's opportunities for that. So saying that previous question you did write 5 over 7, meaning that when you did 1 minus 5 over 7, you get 2 over 7. At least you'd get the answer for C right. They will write CFPA, correct for previous answer. That is also why this second question is only worth 1 mark. I mean, they both look like they have the same amount of work, but part B has quite a bit more thinking towards, whereas C is quite easy, it's just a complementary event. So really, going back to the marking allocation, sorry, that's just 1 mark for that. Here, it's 1 mark for realizing it's 4 over 6 in that second one, and then it's also another mark for multiplying. So even if you multiply the wrong number, you'll still get 1 over 2. So if you did 6 over 7 times 5 over 6, you'll get 5 over 7, and that would get you 1 mark out of 2. Alright, so that's a slightly tricky question, but only because of that one little slip-ups. So yeah, going into question 4 now. 2 ordinary dice are rolled. The score, the sum of the numbers is the score is the sum of the numbers on the top faces. So basically, you roll your 2 dice, add up what it is. So what's the probability that the score is 10? Okay, well, what we should first of all do is think about, well, how many outcomes could there be in total. So let's just start off with that. So total outcomes, and the way to find the total amount of outcomes is to think about how many outcomes there can be in each stage. So here we've got 2 stages. The first stage is rolling the first die, rolling the second die. Even if you roll them at the same time, each of them is a different stage. So when we roll the first die, there's 6. When we roll the second die, there's 6. So there's 36 different outcomes. And that's just 1 mark straight away for somehow getting 36. Okay? But the other thing now is we want to think of all the outcomes where the score is 10. Now to get to 10, so outcomes for 10, the way that you can roll a 10 in this game, okay, is you could obviously roll a 5 and a 5. That's pretty obvious. You can roll a 6 and a 4. And some people will just leave it there. It's like, okay, you roll a 5 and 5 or a 6 and a 4. But you could also roll a 4 and a 6. Because if you did do a tree diagram, and I'm not going to suggest you do a tree diagram here, but if you did a tree diagram here, you'll get there's 6 outcomes for the first one, and branching out of each of those would be 6 of each, so it'd be 36 different things. So what you could do is when you roll a 5 and roll a 5, that's only one thing, but if I roll a 6, I could also roll a 4. If I roll a 4, I could then roll a 6. So there are different things. So from that, we can now find the probability. So the probability of rolling a 10 would be 3 over 36, which equals 1 over 12. Alright, so that's where you get that second mark, by getting 3 over 36, which is 1 over 12. Again, it's not necessary, although when you're doing probability, once you get your final answer, you should probably simplify. It's not hard to simplify 3 over 36, you might as well do it. And now we've got to do, what is the probability that the score is not 10? Well, again, this is a fairly simple question. We just found the probability of getting a 10, so the probability of not getting a 10 is just 1 minus that. So this will take 2 seconds. The probability of not 10 is just going to be 1 minus 1 over 12, which equals 11 over 12. Or if you just kept it as 3 over 36, it would be 33 over 36. Okay, but you should, again, like I said, you should simplify. So that question, that second bit again is kind of depends on your answer from A. So if you got A wrong, but you just did 1 minus your previous answer, then again you'll get CFPA. So make sure, like I've said plenty of times, HSC questions generally tend to build on each other. If you did A, chances are it's going to be useful in question B. Not all the time, but most of the time you'll see that happens. Alright, going to question 5 now. And I'm actually going to do this question twice. I'm going to do this once in a fairly quick way without using a tree diagram, and then I'm going to do it again with a tree diagram. Although the second time with a tree diagram, I'm not going to do the whole question again. I'm probably just going to talk about drawing a tree diagram. So, let's start this off. So we have a total of 300 tickets are sold in a raffle, which has 3 prizes. There's 100 red, 100 green, 100 blue. At the drawing of a raffle, winning tickets are not replaced. So basically, instead of saying it's without replacement. Once you take out the first red, there's now 99 red left over out of 299. We're going to be using that in a second. So what is the probability that each of the 3 winning tickets is red? So what we're trying to do here is we want to find the probability of okay? The probability that it's red and red and red. And again, I said the word and, so therefore I multiply it. So the probability that the first one is red is just going to be 100 over 300. That's fairly simple, alright? There's 300 tickets, 100 over red, 100 over 300. Now, once that's out of the way, because it was without replacement, there are now 99 red tickets in there, out of 299 in total. Okay, so what we've done now is one's been taken out of the total 300, and then again, the probability of the third one being red is going to be 98 over 299. Right, so we're going to get some big fractions here. When you do put that onto your calculator, you'll get a nice small number of 970,200, so 970,200 over 2673,0600, which is 26,730,600. So, big number, but you can also simplify that by just using your calculator. I'm not expecting you to know the hard factor of those two numbers. So when you put that in your calculator and just press equals, you get this slightly more workable numbers. Okay, so this is 2 marks. Basically, your 2 marks are going to be given for realizing that there is a change between each of them, and then the other mark is going to be from multiplying them together. So if you didn't do the change, if you just did 100 over 300 times 100 over 300 times 100 over 300, you still get 1 over 2. Because you realize, well, I've got to multiply 3 probabilities together, but you also need to realize that the probabilities change. Alright? So now we need to find the probability that at least one not red. So if we want to find the probability that at least one is not red, well, this is kind of like a opposite of the at least questions that we normally do. So normally when we have an at least question, it's asking us what's the probability that at least one is red. Well, now we're trying to find the probability that at least one is not red. So the probability of at least one not red. And so the probability of at least one not red, the opposite of at least one not being red is all 3 of them being red. Okay, so normally when we're finding at least one red, we try to think of, well, what's the probability of none of them being red? But because now we're doing at least one not red, the opposite is 3 reds. So this is just going to be 1 minus probability of red, red, red. And guess what we just found in the previous question? So we just do 1 minus our previous answer, which is 42934 over 44551. And again, this is why simplifying in that previous question was pretty handy, because these are just nice small numbers. Alright, so there we go. Just 1 mark for realizing is 1 minus your previous answer. Again, CFPAs come into effect here. If you got A wrong, but you did 1 minus your incorrect answer, you'd still get B right. And then lastly, question C. So what we want to do, I should go up to the question. What is the probability that there is at least one winning ticket of each color? Sorry, not at least one. That there is one winning ticket of each color, and that's a massive distinction actually. The first thing I said would have actually been quite hard to find. So what is the probability that there is one winning ticket of each color? So what we need to do here is think about all the different combinations that can happen if they're all going to be different colors. Because basically what we're saying is there needs to be one red, one blue, and one green. But the order doesn't matter, okay? So what we're trying to do here is all the... So the outcomes here are, well, it could be red, green, blue, or it could be red, blue, green, or it could be green, red, blue, or it could be green, blue, red, or it could be blue, green, red, or it could be blue, red, green. So these are the 6 different ways that we can get all of them being different colors. And so, again, a quicker way that you can found the amount of outcomes that fit this situation is think about, just for the colors for a second, these are 3 stages. Each ticket is a different stage. So in the first stage, there are 3 colors we could have chosen from. There are 3 stages we could have chosen from. Then, say I chose red in the first one, that means there's only 2 other colors that I could have chosen from. It doesn't matter which color I choose first. In the second one, there's now only 2 colors I could choose from. And lastly, there's only 1 color I can choose from. There's 6. So there's 6 different ways, which we kind of just listed out here. There's my 6 different ways of getting each of those. So now, what we're going to do is we're going to find the probability of getting a red, a green, then a blue. Or a red, then a blue, then a green. Or a green, then a red, then a blue. And then a green, and a blue, and a red. And like so on. So what we're going to need to do is find the probability of each one of those happening, and then add them all up. Fortunately, they actually will be all the same. Okay, it doesn't matter which order you do it in, the probabilities of them is all going to be the same. So we're just going to actually just times it by 6. So here, the probability of different colors, I guess, the different colors, is going to be 6 times the probability of, let's just choose one, red, green, blue. Alright, choose the first one. So it's 6 times because, and you can do this yourself, you can do the probability of all 6 things, but you'll see that the probabilities are all the same. And so the probability of getting a red first, is 100 over 300, as we talked about earlier. The probability of then getting a green is going to be 100 over 299. Because yes, there are 299 tickets left in the thing, but there's still 100 greens. Until we get a red, I haven't changed the greens. And then lastly, this is 100 over 298. And then so when you put that into your calculator, simplify and all that kind of stuff, you'll get 6 with that number, an extra 0, yep. So 6 million over 26,730,600. And that can probably simplify, but whatever. I mean, like, one thing you could simplify straight away is get rid of zeros. You can simplify that further, but whatever. So what I'm trying to say here is, if you did find the probability of each of these, like this would also be 100 over 300 times 100 over 299 times 100 over 298. Same with that one, same with that one, same with that one, same with that one, and obviously so with that one. So because they're all going to have the same probabilities no matter which way you do the order, rather than finding orders and adding them all up, just realize we can just do 6 times it. I wouldn't recommend always trying to look for those kinds of shortcuts because they're not always going to work. But when you do start to see them happening, you might as well do it. Okay. So, like I said, I want to do this question again just really quickly. Except I'm going to set up a tree diagram, and I'm not going to do the whole question again with a tree diagram. But I'm hoping that if you were to see a tree diagram in front of you, you'd be able to maybe go from there. The reason why I didn't, I would rather just do it this way, is because we see all the working isn't too much. It's like, 2 lines there, maybe have 3 or 4 lines there. So not too much work. Whereas if I did a tree diagram, not only is the tree diagram going to be quite large, but then reading that tree diagram is always going to be a bit tricky and whatever. So I'm going to leave myself quite a bit of space because, as some people found out when doing this question in the test, there's going to be 27 different things that can happen. The way I know there's going to be 27 is, I mean, how many colors can you choose in the first raffle? Well, 3. How many can you choose in the second draw? 3, because we're now not talking about each of them being different colors, so it doesn't matter. And then how many things are there in the third? 3. So there's 27 different outcomes that you can get when we do a tree diagram, and that's going to be a pain in the butt. But we'll do it anyway, just to see what it would look like. I want to kind of illustrate why tree diagrams aren't always going to be the best thing to do. So remember, tree diagrams always start at a central spot, and the first draw, I'm going to give myself quite a bit of space, and I don't think even that's going to be enough space, but whatever. So the first thing that can happen is going to be red, blue, or green. Okay? And each of these is 100 over 300, 100 over 300, and 100 over 3. That's good. Alright, that's the first draw. Now if I chose a red first, I could then choose a red, a blue, or a green. If I chose a blue first, I could choose a red, a blue, or a green. I'm going to start to see the problem I'm going to run into in a second. And if I do down here, a red, a blue, or a green. And now on the third draw, and this is where students also kind of found, oh, this is going to be a pain in the butt, is because now I'm going to have to draw these ones out into red, blue, or green. Red, blue, green. Red, blue, green. Red, blue, green. Red, blue, green. Red. I'm not even going to continue at this point because I feel like it's, I might as well continue, but just to kind of illustrate how annoying this is. Because out of each of these, not only do I need to do all of this, I'll then do red, blue, green, red, blue, green, red, blue, green, red, blue, green, red, and so on and so forth. And then each of these, I'm now going to have to list out all of these. So this is red, red, red. This is red, red, blue. This is red, red, green. This is red, blue, red. This is red, blue, blue, and so on and so forth. Like, I'm going to have to list out 27 different things. And when I'm listing out 27 different things with each of 3 letters, I'm writing 81 different letters just to list out the whole sample space. It's going to be a pain in the butt. And that's not even considering the fact that I've also got to calculate the probabilities of each of these things. So tree diagrams are not always going to be the most, the best things to do. And so my recommendation would be, look, if you like doing tree diagrams, by all means do so. But the second you start thinking, oh wow, this tree diagram is getting quite large, that's probably an indicator you probably shouldn't be doing a tree diagram in the first place. Just think about the specific situations that you need to be, thinking about. So when I was doing red, 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 yeah, I could have done this whole tree diagram only to look down this path. Alright? Sure, it's the top one if you're doing that order, but it didn't need to be. It could have been the bottom one as well. So, red, red, red could just be seen through just that one path. Part B would have just been seeing the same thing, and part C, yeah, you could have listed out all the things, count them all up. Oh, there's 6 of them, so 6 times. But at that point, you've wasted a lot of time. You probably have a really ugly page. You're frustrated because you just spent 5 to 10 minutes doing this tree diagram, which you barely even used. Alright, so moral of the story: if your tree diagram is starting to get too big, it probably is too big. Alright, just stop yourself there. Think about what the question is asking you to do. Alright, so it's a bit of a rant on question 5, and so let's just finish up with question 6. A pack of 52 cards consists of 4 suits with 13 cards in each suit. One card is drawn from the pack and kept on the table. A second card is drawn and put sub table as a probability. The second card is from a different suit to the first. So, what we're trying to do is find the probability that it's different to the first. So, probability it's different. Well, if I put one card on the table, so I have 52 cards, and when I've taken one card and put it on the table, I now have 51 cards. Okay? And so now 13 cards in each suit. So let's say I took out a diamond. That means I'm going to get rid of the rest of the diamonds. Meaning I still have 13 hearts, 13 clubs, 13 spades. meaning I have 39 other cards left over. So the probability that's not the same is 39 over 51. Fairly simple. Okay, it's just one mark. Generally, one mark means you really just looking for one thing. And the 2 cards are replaced and the pack is shuffled. 4 cards are chosen from the pack and placed side by side. Was the probability that these 4 cards are from different suits. So it's kind of the same thing now, except no, it's now not just 2 things. It's now 4 different things. So what we're doing is probability of all different. And let's just think about this for a second. So it might help if I draw it to the side again. So let's say I've got my, excuse this drawing, this is going to be shocking, but say I've got my clubs, I've got my, no, that was the spades, I've got my clubs, I've got my hearts, and I've got my diamonds. Okay? So this is kind of like the soft thing. It doesn't matter what I choose first. Okay, if I choose a spades first, then I've just chosen the spades first. It doesn't really matter. So we're not really thinking about what's happening in the first one. We need to start thinking about what happens after the second one. So once I've drawn, I put the first one on the table. Let's say I put down a spades first. So now there are 3 suits that I can be choosing from now, out of 51 cards in total. So there's still 51 cards, so I've only taken 1 card away, but now I'm looking for 39 cards left over. And now, what we're saying is and, so you want to see that the next one is different, so it's going to be different and different and different. So multiplication again. So let's say I chose a hearts second. So now I've got 2 cards on the table. So now I have 50 cards still in the pack, 2 cards on the table. But now I'm really looking at 2 suits. So there are 26 cards in those 2 suits. So it's not going to be 38, because what you're doing there is you're kind of thinking about no spades and then that 1 heart that's opened out. No, we're now just including all the hearts as well. And then lastly, let's say I took out a diamond. So now there's 49 cards in here. And of those 49 cards, only 13 of them are going to be clubs. So this is the thing we get. We want to find that we don't care about what happens first, because it doesn't matter what happens. But the probability that the second card we draw of the other 3 suits is going to be 39 over 51. And then the next one will be 26 over 50. Then the next one will be 13 over 49. So they need to be different suits all the time. And then so when we multiply these all together, we get 13,182 over, what's this, 124,950. And so just multiplying them again. So the 2 marks for this question would be given, first of all, realizing that these numbers at the bottom change, and then also realizing that they're getting the correct numbers in the top. So basically, you can't really get this bottom line without getting that top line right. So basically, 1 mark for the denominators changing appropriately, and 1 mark for the numerators changing appropriately. Or obviously, you just get right to the final answer, but that would be pretty rare. You wouldn't do that without doing that. Anyway, so this is the end of the quiz. I think what we can take away from this video is, first of all, you really need to read the question carefully and think about what it's asking you to do. The second thing you need to take away from it is, if in part A it asks you to find something and part B kind of sounds the same but a little bit different, it means they're probably linked to each other. So there were lots of questions where it was like 1 minus your previous answer or something. So generally try to look out for like common languages, so you can kind of see, oh, okay, it's probably going to ask me to use the previous answer. And the third thing, and probably the most important thing with regards to time management, is try to save yourself from drawing these massive tree diagrams. They're not always necessary. Unless the question says draw a tree diagram, like it tells you must, then of course you have to. But otherwise, they're not necessary. They might be helpful, but again, if we get to a tree diagram looking like that, and I didn't finish that and I kind of gave up, it means you've probably done something which is inefficient. It works. I mean, it'll just take 10 minutes to do it all properly, when you could have just done it in like 2 seconds. Anyway, hopefully that these videos have been, this video solution has been useful, and if you have any more questions, make sure you ask. Thanks for watching.